Hello and welcome to what may very well be your first FST notes video. For Chapter 1, Section 1, there is a lot of things to read, so I'm not going to necessarily go through those. You may want to pause. I'm going to try to go fairly quickly because there's 23 slides, so remember it is a video, so feel free to rewind as well. We do have several objectives to take a look at here. Writing sets using set notation. We'll take a look at number lines. We'll talk about the different sets of numbers, a little bit about what additive inverses are, we'll talk absolute value, inequalities, and graphing sets of real numbers. So a wide range of ideas here. Starting off with those different sets of numbers, or even what a set is. A set is a collection of objects. The objects are called elements or members of the set. Usually we use set braces in order to enclose the elements of a set. Set like 1, 2, 3 is what we call a finite set, meaning it has a beginning and an end. It's not infinite. Natural numbers is kind of the first set of numbers that children learn, starting with 1, going to 2, 3, 4, 5, 6, and so on. They do go on forever, so that is not a finite set. The 3 dots here, they're called ellipsis points, show that it continues indefinitely. So that's an infinite set. Counting numbers, natural numbers, it's the same thing, just different ways of saying the same thing. Whole numbers, those just include 0. So for this text, when you see n in this context, that's referring to the natural set of natural numbers. W refers to the set of whole numbers. If a set contains no elements, like the whole numbers less than 0, that's the empty or null set. There's 2 different ways you can usually write that, either like this or like this. Little note at the bottom, do not put those 2 symbols together for the empty set. That's actually the set with 1 element, which is the symbol for the empty set, so it's not quite the same thing. Here's some more notation. Again, just take some time, probably just pause the video and go through that quickly to see what some of those symbols are. I'm not going to take too much of your time to go over those, but go ahead and read that. Here's some notation that we use quite a bit. It's called set builder notation. They kind of go through the we've got an example here and then kind of just general how that's set up. So it's the set of, and that's what the outer brackets are, saying this is a set, so the whole thing is a set. All elements, x. So typically it's just a plain x, but there are cases where maybe it's x over y or x plus 2, but this doesn't always just have to be x. And then we explain the characteristics of x and any other variables that we have. So that's all elements x such that x has whatever property we want. So for example, they're describing a set where the set is all values x such that x is a natural number between 3 and 15. So that would be like 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 would be that set. You got to be careful when they're using between. So this set does not include 3 or 15. So basically it's the natural numbers from 4 to 14. And again, when you say from, then that gets to be a little bit unclear. So we want to be clear, so we'll use between. So listing the elements in sets. So that's one of the objectives that we want to be able to do. So given a set builder notation, can I list the numbers that are in that set? So the set of all elements x such that x is a natural number less than 4. So we got to remember first of all what the natural numbers are, and then we have to understand that they're less than 4, so not including 4. So natural numbers less than 4, that's 1, 2, 3. Write that answer in set notation. Second example, the set of all values y such that y is one of the first 5 even natural numbers. So first 5 even natural numbers. So again, we got to know what even means. We got to know what natural numbers are. So 2 is the first even natural number. 2, 4, 6, 8, 10. That's 5 of them. And that's how we would, those are the elements in that set. And then the last example, the set of all elements z such that z is a natural number greater than or equal to 7. Okay, so again, set of natural numbers greater than or equal to 7. That's an infinite set. So we have ellipsis points there. See how, again, those are at the end. We do enough to establish a pattern, 7, 8, 9, 10, dot, dot, dot. And again, you don't have to, you could probably get away with 3 if you go 7, 8, 9, dot, dot, dot. You could do more. It's not a problem as long as you have the ellipsis points at the end. Here's a problem for you to give a shot at. So if you want to go ahead and pause it, then do this, and then I'm going to go ahead and do this as well. Alright, so x such that x is a natural number less than 6. So I start with my set bracket. Natural numbers start with 1. We go 2, 3, 4, 5. Again, do we include 6 or not? Well, again, it's numbers less than 6. So 5 is the biggest number in that set. So 1, 2, 3, 4, 5. Here's, again, part of the objective of being able to deal with sets is now working with this the other way around. Given the set, now write it in set builder notation. There are some kind of common tricks that we can use here. You're going to want to kind of get a feel for how the easier ways are to use the language in order to describe this set, and only this set, so you're not describing extra things that make it so that your answer is wrong. There are several ways that you can do that. This is probably one of the best ways. So again, we start with our set brackets, just a y, you could use an x, you could use a z, you could use whatever really, but just pick a letter. So the set of all elements y such that y is one of the first 5 odd natural numbers. Again, very common trick. First 5 odd, and then natural numbers for a set of numbers there. Again, that includes just those 5 numbers, 1, 3, 5, 7, and 9. A pretty slick way to describe that. Getting a set like this one, 5, 10, 15, with the ellipsis points, that goes on indefinitely. So notice what they do here. It's the set of all elements x such that x is a multiple of 5 that's greater than 0. Again, notice they don't have to mention natural numbers. We just mentioned multiple of 5 that's greater than 0. So again, the greater than 0 is necessary. You can't just say a multiple of 5 because 0 is also a multiple of 5 and it's not in this set. So again, the greater than 0 is required there, but multiple of 5, kind of the trick for making that one fairly easy. There's 2 for you to try at the bottom. Again, writing each set using set builder notation. So again, if you want to pause the video, I'll go ahead and do those as well. Alright, so I went ahead and wrote out my answers already. Please forgive my handwriting, it's bad enough as it is, much less trying to write on the screen here. So I'll go and read that as well. So for the 2, 4, 6, 8, one way you can do that is to say the set of all elements x such that x is one of the first 4 even natural numbers. Now with evens, you can also say multiple of 2, although, again, then you gotta somehow limit it. So that multiple works really well when you're just talking an indefinite set, but with this one, since it's finite, a little bit easier just to do one of the first 4 even natural numbers. For 15 there, the 4, 8, 12, 16, again, because it continues on, and 4, 8, 12, and 16 are all multiples of 4, then saying that it's the set of all elements x such that x is a multiple of 4 that's greater than 0, then that covers everything you need for that set. Again, I'm not going to spend too much time on this. It talks about positive numbers, negative numbers, integers. Talks about graphing things on a number line. I will emphasize this here. Notice this set for integers, or sorry, not integers, but rational numbers. Notice the p over q. This is one of the few times we get to see the set notation where it's not just a p or a q or an x. It's a p over q. And then the condition is that p and q both have to be integers, and q can't be 0. Of course, the problem there is if q were 0, then you'd have whatever p is divided by 0, which would be undefined. And that, of course, is not a rational number. So if you want to pause so you can read through the rest of that, feel free. This slide gets into, again, the idea of what irrational numbers are. Again, there's a bit there that you can read as well. And then you take the rational numbers and irrational numbers, put those together, we get real numbers. Again, they've got an example of different types of rational numbers, and then they've got some irrational ones there as well, plotted on a number line. So again, if you want to pause and take a look at that in more detail, you can go ahead. Here are a few different ways to try to help you remember the different common sets of numbers. So we've got basically just a list here, the name, and then a description or set notation. I really like this one because it shows kind of the relationship between the natural numbers, whole numbers, integers, and rationals. Also the rational and irrational numbers comprising the reals. Personally, I don't like this one so much. Maybe you will, so I included that as well. Again, if you want to pause that so you can study that a bit more or refer back to it later, feel free to go ahead. Again, here we have a set of numbers and then some different questions. Which numbers in this set are elements of the integers? Well, we got -8, 0, and 2 are integers. So again, just a way to practice knowing which numbers go in which set. So again, if you want to pause and take a look at that, we've got some, again, questions, answers here. Another one that we have here as well. We'll go through this in class. If you need some more help on that, let me know, but I don't think I'm going to actually do this one here. In order to help us think about those different sets of numbers, we've got some true-false questions. Again, these have got the answers here, so we'll go through those, and then one for you to think about here. So all irrational numbers are real numbers. So that's true. If a number is irrational, then it is real. You can see in that figure 4, which was a couple slides ago at this point, instead of real numbers include all the irrational numbers. So that is true. Every rational number is an integer. Well, that's false. And if you remember from geometry, the only thing you need to show that a statement is false is a counterexample. So some rational numbers are integers. That's true. But this says that every rational number is an integer. So rational numbers like 2/3, -1/4, they're not integers. And then they've got the example, every integer is a whole number. Again, if you want to pause and think about that, see if you come up with the right answer. I'm just going to go ahead. So again, it's similar to B here. There are integers that are whole numbers, but integers also include negatives like -1, -2, -3. Those are not whole numbers. So kind of the same deal as this one. We can come up with some counterexamples to show that that is false. And again, if it's false, we should be able to tell why. Again, we've got a bit of information here, just adding negatives basically. And so for every real number, A, you've got the opposite of A, that's the additive inverse. So you can have a number like a -9 or a -15. So -4 is the additive inverse of 4, or you can have like 12 - 3. So we use that negative a few different ways. Again, one thing to keep in mind, like minus a -5, that's actually the same as 5. And oftentimes the way I think of that is the opposite of -5, and that is 5. So sometimes, very common for people to let negatives kind of mess them up. So again, if you want to take some time to read through that a little bit more carefully, feel free to go ahead. But we always have to be very careful with negatives. Don't lose points just because we mishandle those. All right, so absolute values, sometimes people have a hard time with this. So the absolute value, geometrically, I think is a good way to think of it. Absolute value of a number A, written like this, is the distance on the number line from 0 to A. So whether you're looking at 5 or -5, they're both 5 units from 0. So the absolute value of -5 is 5, and the absolute value of 5 is 5. The absolute value of a number cannot be negative. It represents distance, so it cannot be negative. But that doesn't mean it's always positive, like the absolute value of 0 is 0. so you got to be careful with that. But again, absolute value, some people think it just kind of makes the number positive, and that's kind of a simplistic idea of what it does, and it's pretty accurate. You just have to be careful sometimes thinking of it that way. So we got kind of some fairly simple relationships explained here. Again, these are all done already for you to kind of just look at and follow through, and then some more for you to try here. So I'm going to go through and do these. If you want to pause and work on those yourself as well, then I'll continue. And again, I recommend taking some time to look at these as well while you've got the video paused. All right, so I've got these finished here. So 43, we have just 8. It's the absolute value of -8. Contrast that with 47, where the negative is on the outside, and the absolute value of 5 is just 5, but then we get the opposite of that, so a -5. 49 includes 2 negatives, but really the absolute value of -2 is 2, and then we get the opposite of 2, so a -2. Here we do the absolute value of -2 and the absolute value of 3, so we get 2 plus 3. We add those together, we get 5. So there's a bit of order of operations there as well. Here we're looking at projected annual rates of change, and they basically ask which of these expected to see the greatest change and the least change. Well, when you're talking greatest and least change, it doesn't matter whether it's going up or down. So greatest change would be the cut and sew apparel manufacturing. So even though that's a negative, it's still the greatest amount of change that we have. And again, if you want to pause and take a little more time to read, that's fine. Same kind of thing here. Which city had the greatest change in population? What was the change? Was it an increase or a decline? And again, we can see the percentage change. We don't actually know the raw number change. But the one with the greatest amount of change would have been Las Vegas, 11.5% change. That was the biggest percentage of change that they have. And then the least change in population, we'd be looking at Chicago going down 1.2. Looking at inequalities, again, just kind of a reminder what that looks like. So an equation like 4 plus 2 equals 6, it's a statement that two quantities are equal. Anything other than an equal sign that has one of these symbols is an inequality. 4 doesn't equal 6. It's not an inequality we use very much, but that's an inequality. And then we've got our less than symbol. So 8 is less than 9, -6 is less than 15, -6 is less than -1, 0 is less than 4/3. So those are all less than symbols. And then you've got the greater than symbol. 12 is greater than 5, 9 is greater than -2, -4 is greater than -6, and 6/5 is greater than 0. Notice the symbol always points toward the smaller number, so the small pointy end is pointing towards the small number. The big end is by the big number. And we can also compare them on a number line. The smaller of two numbers is always on the left, to the left of the other number on a number line. Again, you may want to pause to get some more time to look this stuff over. I will just emphasize, be very careful when ordering negative numbers. It may help to think about putting those on a number line. Again, here's some good information you may want to just pause so you can take in and read all of that. Again, I'll just emphasize the symbols, these inequality symbols. We also have the less than or equal to and greater than or equal to. So here we've got an inequality that we're trying to determine whether it's true or false. Really, to be able to do that, we have to simplify it first. So there's not a lot to be done, but we can do the 2 times 5. That gives us 10. And then that's greater than or equal to 4 plus 6, which is also 10. Now, they kind of explain this here. When we've got the equal to, as long as either the inequality part or the equal to is true, then it's true, because it's greater than or equal to. So 10 is equal to 10, so that is a true statement. Here's a slightly different way to graph an inequality. So we've got the inequality written in set notation, set of all values of x, such that x is greater than -2. Notice they don't mention any sort of natural numbers or whole numbers, so we're talking all real numbers. And we used to do like an open circle here. This is an improvement on that, where instead of the open circle we use a rounded parenthesis. Just to throw this in there, if it were instead, so again I'm changing this intentionally, if this had the equal to, so you can kind of get that in the right place, then instead of a parenthesis it would be a bracket. One of the reasons this is a little bit better than the open or closed circles is because you can tell which direction the bracket is pointing. The bracket is pointing to the right, which is where the answers or solutions to that inequality, numbers that are in that set, in this case I suppose, are. Whereas the open and closed circles, you can't point them in a certain direction because they're circles. They don't point anywhere. So that's how we can graph that. We can also write that in interval notation. Now again, this is based on their original one that didn't have the equal to. So notice how we also have a parenthesis here. And in that we've got just the minimum number in that set, the -2, which again isn't actually in the set because the parenthesis, the -2, isn't included. And it goes up forever, so up to infinity. That'll always have a parenthesis whether this has got an equal to or not. So for mine, the way that one would look when I changed that to have the equal to, then that would just be -2. That's a negative, there we go. That's a funny looking comma, but you'll forgive me, I think. So -2 to infinity, that's what that would look like for my change on that one. Notice again, even though the -2 has a bracket, the infinity has a parenthesis. Infinities are not actually numbers, they're just ideas, so they can't actually be included in that number set. So here's another example of that. They give us the set builder notation, set of all elements x such that x is less than 4. Write it in interval notation and graph the interval. Again, this is another one of our objectives, is to be able to do this. So the interval is this way, -infinity up to 4. And I would kind of maybe do this the other way. To me it's easier once you graph it to come up with the interval notation. You can kind of do that however you want. Here's one for you to try. So if you want to pause so you can get that done, I'll go ahead and work on that as well. So here's what my answer looks like, and again, I didn't do the fanciest number line, I just have 0 and 1 on there. But I've got the parenthesis at 1 facing to the right, because it's the values that are greater than 1, and then in my interval notation, parenthesis, and then 1, comma, infinity with another parenthesis would be the interval notation for that one. This is the same kind of thing, just with the equal to instead. Again, so if you want to pause and look at that one, and then at the same time go ahead and do this 103 here, I'll do the same. So here's what mine turned out to look like. Again, a very simple number line. I've got 5 and 6 on there. Bracket at 6 facing to the left. Mine was a little off, but again, hopefully you'll forgive me for that as well. And then the interval notation, again, the -infinity goes on the left, and that has a parenthesis to the left of that, and then a bracket on the 6 to show that the 6 is included. And here we've got what we call a 3-part inequality. Notice in the set builder notation, it's the set of all values x such that -2 is less than x and x is less than 4. It's really all real numbers between -2 and 4. In interval notation, it looks like an ordered pair here, so that's why we got to understand based on context. This is interval notation. It's not the ordered pair -2, 4, which you would graph on the Cartesian coordinate grid 2 units to the left of the origin, 4 units above the origin. Okay, it's the interval from -2 to 4, not including those values. So that's the interval notation, and then of course here's the graph. Here's another example of that, mixing with the equal to and the not equal to, basically from 3 to 10. And again, notice the interval notation there. So we get a bracket at 10 facing to the left, a parenthesis at 3 facing to the right, and then there's a problem here at the bottom for you to try. So if you want to pause, take a look at that stuff, and do number 109 there, I will do the same, and then that will be the end of this video. Alright, so here's what my graph and interval notation look like. So parenthesis at -4, bracket at 3, facing together, we connect those, and then the interval notation, just parenthesis -4, comma 3 bracket, and that is it. Well, thank you very much for watching. Hopefully you found this to be useful. If you have any questions, feel free to let me know.